So yesterday we started talking about related rates videos, and we specifically focused on problems that would use the Pythagorean theorem for the equation in the problem. Today we're going to look at problems that use trigonometry or area and volume formulas. So if we go back in our notes to that page where we were keeping track of what formulas might be useful, another type of formula besides the Pythagorean theorem that would be useful is trigonometric formulas. So think about SOHCAHTOA. You're going to know that you need to use trigonometry formulas when it starts talking about angles, because angles are really closely related to trigonometry. All right, let's take a look at this problem. This is an actual AP FRQ question. Ship A, here it is traveling due west towards a lighthouse. So ship A is going this way at a speed of 15 kilometers per hour. Ship B is traveling due north. B is going this way at away from the lighthouse at a speed of 10 kilometers per hour. Let x be the distance between ship A and the lighthouse and at any time. So it's giving me a picture. For part A, it says find the distance between A and B when x is 4 and y is 3. Well, if I think about this triangle, and I know that y is 3 and x is 4, because I've heard of 3, 4, 5 triangles before, I know that this side must be 5. So I would say that the distance is equal to 5 kilometers. Now let's say I didn't remember 3, 4, 5 triangles. If I didn't remember, I could always set it up as 3 squared plus 4 squared equals our distance squared, which means 9 plus 16 equals distance squared. So 25 equals distance squared, which means my distance would be 5. I could always do Pythagorean theorem to figure that out. I find that knowing a 3, 4, 5 triangle is very useful there. Next, find the rate of change in kilometers per hour of the distance between the two ships when x is 4 and y is 3. As soon as I see rate of change, I'm thinking we need a derivative. So again, the same way that I set up Pythagorean theorem here, I'm going to set up Pythagorean theorem but without filling in the numbers 3 and 4. So this is going to be a related rates question. We've got y, we've got x, and we've got this distance. So I'm going to make a list of my variables: x, y, d, dx dt, dy dt, dd dt. Because in this problem, all 3 of these variables are changing. Both boats are moving, and that means their distance between each other is changing. Now at this moment in time, x is 4, y is 3, and we just calculated that the distance is 5. We also know from the original problem that ship A is traveling towards the lighthouse at a speed of 15. So if this guy's going towards the lighthouse at a speed of 15, then his distance is changing at negative 15 kilometers per hour. Now again, I'm making this negative because that distance is going to get shorter as the boat gets closer. Dy dt, this ship is sailing upwards at 10 kilometers per hour. So his distance is getting bigger by 10 kilometers per hour, and we don't know how fast the distance between the ships is changing because that's what we're trying to figure out. Now that means that first we're going to set up Pythagorean theorem. X squared plus y squared equals distance squared. Then we're going to take the derivative. So 2x dx dt plus 2y dy dt equals 2d dd dt. Ooh, you can't see what I'm writing. Let's just pause for a second, let you guys take a look at that. Every single one of these variables is changing with respect to time. The boats are sailing, their distances are changing, therefore when you take their derivatives, they all have to be changing with respect to time. Now let's fill in the numbers. Remember, we never fill in the numbers till we take the derivative. After the derivative is over, we can fill in the numbers. So we've got 2 times 4 times negative 15 plus 2 times 3 times 10 equals 2 times 5 dt. Now let's simplify that. We've got 8. Actually, you know what? I'm going to do 4 times 15, which is 60. So I've got negative 120 plus 2 times 3 is 6, so 60, equals 10 dt, which means I get negative 60 equals 10 dt. So dt equals negative 6 kilometers per hour. The boat's distances between them is negative, is decreasing. So in other words, they're getting closer together by 6 kilometers per hour. Now this all should kind of remind you of what we did yesterday, but here's where we change things up and we use a trig formula. You'll notice in part C the problem starts by saying, let theta be the angle shown in the figure. All of a sudden we're talking about an angle. That's your clue. You're probably going to need a trig formula. Find the rate of change of theta in radians per hour when x is 4 and y is 3. So we've got this triangle. It told us in the original problem theta was this angle. We've got x, we've got y. Because it specifically gives me the values for x and y in the directions, I'm going to try to set up some sort of a trig formula with these 3 variables, and I'm going to ignore the distance, the d value, for now. Now, in respect to this angle, this side of the triangle would be the opposite side, and this side of the triangle would be the adjacent side. So the formula I'm going to set up in this problem is tangent. Let's list our variables, theta, x, and y, and let's list their derivatives, d theta dt, dx dt, dy dt. Now I know x is 4, I know y is 3, I know that dx dt is negative 15, I know dy dt is 10. This is all something that I've gone over because I already did the other 2 parts of the problem. Alright, so let's set up a formula here. We know that our formula for tangent would be that the tangent of our angle equals the opposite over the adjacent. Oh, yeah. So, next we need to take a derivative. The derivative of tangent is secant squared of theta times d theta dt equals, and here's where it gets tricky. You need to use quotient rule. So low d high minus high d low, and low squared goes down below. Now we can fill in what we know. So, the first question, and the easier question, is filling in these numbers. 4 times 10 minus 3 times negative 15 all over 4 squared. Those are easier numbers to fill in simply because we already know them. We know that d theta dt is what we're trying to find, so we're not going to have a number to fill in there. Instead, let's try to figure out secant. Now, secant of theta, how can you possibly do this without a calculator? How do you find secant? Well, as a side note, let's make a note. Secant is 1 over cosine, which means instead of cosine, which is adjacent over hypotenuse, it's going to be hypotenuse over adjacent. Because of the work we did in the previous parts of the problem, I know that the length of this hypotenuse is 5. We figured that out in part A, and we used it again in part B. So the hypotenuse would be 5 over the adjacent is x, which is 4. Don't forget to square it, because our formula for derivative of tangent isn't just secant, it's secant squared. This, using hypotenuse over adjacent, is the way I calculate this ratio right here without a calculator. Now let's simplify. 5 over 4 squared is 25 over 16, d theta dt. 40 plus 45, which is going to be 85, divided by 16. And finally, I'm just going to multiply by 16 over 25 to make this cancel. So d theta dt will equal, the 16s cancel. If we divide by 5, we get 17 over 5. And we're measuring in radians per hour, so it would be radians per hour. This part C is really the new stuff today, and it's the idea that sometimes we set up a trig formula to solve one of these problems, and that when you set up a trig formula to find the value of other trigonometric equations that are going to come up in the problem, because we're going to have to take derivatives, we use ratios like from SOHCAHTOA. All right, the second type of problem we're going to look at today is area and volume formula problems. So just like we needed to be able to use trig formulas to solve these problems, we're going to need to be able to know area and volume formulas, which means we're going to have to know the area and volume formulas. So let's start with number 1. A crowd gathers around a movie star forming a circle. The radius of the crowd is increasing at a rate of 3 feet per second. How fast is the area of the crowd increasing when the radius is 15? Remember, this radius is forming, this crowd is forming a circle. So if we draw a circle and we label the R is getting bigger, therefore the area is getting bigger. So because I'm going to be measuring the area, and I've got the radius as a variable in the problem, I would list dA dt and dr dt and a and r as my variables. Now it says that the radius of the crowd is increasing at a rate of 3 feet per second. So 3 feet per second. How fast is the area taken up by the crowd increasing when the radius is 15 feet? So my area formula for a circle is pi r squared. If I take the derivative, I get dA dt equals 2 pi r dr dt. Now I'm going to plug in my numbers. So dA dt is what I'm kind of trying to figure out here. 2 pi times 15 times 3. And now if I simplify, 2 times 15 is 30 times 3 is 90. So the area of the circle that's being occupied is increasing at 90 pi feet squared per second. Now it's important to realize that the units here would be squared because we're measuring an area, not a distance. So area is always squared units. Let's talk now about cubes. A hypothetical cube, meaning we're just imagining this, grows at a rate of 64 meters cubed per minute. How fast are the sides of the cube increasing when the sides are 3 meters each? So let's draw a cube. The key thing about a cube is that all of the sides of a cube are the same size. So S, 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 which means the volume of the cube is only related to S. There's no length times width times height because it's all the same thing. So dV dt, ds dt. It says here the sides are 3 meters each, and it's growing at a rate of 64 meters cubed per minute. That means that we know the change in the volume. Now, let's set up our volume formula. The volume of a cube would be s cubed. dv dt equals 3s squared ds dt. If we fill in what we know, we get 64 equals 3 times 3 squared ds dt. So, we get 64 equals 27 ds dt. So ds dt equals, let's see, 64 over 27, and it would be meters per minute. Yeah, because we're just measuring the length of the side. Last but not least, let's talk about spheres. So let's write down some formulas we just reviewed. The area of a circle is pi r squared. The volume of a cube is s cubed. We're going to do the volume of a sphere, we'll write this down, is 4/3 pi r cubed. Bloop, 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 bloop. Try to turn it right way. And we're going to do that the surface area of a sphere is 4 pi r squared. Those are kind of common ones that come up a lot that I think we sometimes have trouble remembering, so let's make sure we remember those. Alright, so a spherical balloon has been inflated so that its radius is increasing at a rate of 4 centimeters cubed per second. How fast is the volume of the balloon increasing when the radius is 5? I'm talking about a spherical balloon, and we're talking about the volume changing with respect to the radius. Now, if volume and radius are my variables, then I'm going to list their derivatives and the variables after I write down the formula. So, what do I know? I know that the radius is increasing at a rate of, the volume. No, this shouldn't be cubed because this is supposed to be radius. Sorry about that. That was a typo. The radius is increasing at a rate of 4 centimeters per second. I know that right now the radius is 5 centimeters, and I want to know how fast the volume is increasing. So first, my volume formula would be 4/3 pi r cubed. Now dv dt would equal 4 pi r squared dr dt. I'm just taking a derivative, making sure to put dt's when necessary. If I fill in what I know, dv dt would equal 4 pi times 5 squared times 4. Now 5 squared is 25, so I would have dv dt equals 25 times 4 is 100, times another 4 would be 400 pi. And since I measure volume in cubic units, it would be cubic centimeters per second. And that's my answer. So 2 different types of problems that we're exploring today. We're exploring problems that require us to use trigonometry to solve them, and we're exploring problems that require us to use area and volume formulas to solve them. So far, those are the big 3 varieties that we've talked about: Pythagorean Theorem, trigonometry, area, and volume. We have 2 more varieties left, and those are the 2 that are very kind of specific, so we will go over those in tomorrow's video, and I will see you tomorrow.